the notes for AP Calculus on the topic of slope fields. So slope fields, remember, are a graphical representation of what the graph of the original function could look like given a derivative like we have right here. And what you do is you draw at each of these points. If the graph were to go through these points, you draw a little tiny tangent line or mini tangent line. So you get an idea of what the slope of the graph would look like if it goes through that point. So you could substitute in one point at a time here. In this case, we've got 12 different points. However, it's probably easier if you try to find any horizontal or vertical tangent lines first. So for the horizontal ones, you want the numerator equals 0. And here, notice if you add the y over, you get y equals 1. So when y equals 1, we'll have horizontal tangent lines. And then if there is a denominator, which in this case there is, then you could also have vertical tangent lines. So if you set the denominator equal to 0, add the 2 over, you get x equals 2. So at x equals 2, we'll have vertical tangent lines, because that's going to make the denominator 0, making it the derivative undefined. However, if both of those are 0, if y equals 1 and x equals 2 at the same time, then it means both the numerator and denominator 0, which is indeterminate. And that means you draw nothing. Because it could mean one of two things. One thing it could mean is that the original function would never go through that point. Hence, there would be no tangent line to draw. Or, if it does go through the point, that the derivative doesn't exist there. So there is no tangent line. That's the other possibility. So in this case, at 2, 1, so at 2, 1, if you want, you can initially put a little circle there to remind yourself you're not going to draw anything there. The graph will never go through that point. So then for the horizontal ones, y can be 1, and as long as x is not 2, so you don't get 0 over 0, then we'll have horizontal tangent lines, so we can draw those in here. When y is 1 would be all these points except for this one where x is 2. So it doesn't matter how long you draw them, just don't draw them so long that they're going to intersect with each other. And when x equals 2, as long as y is not 1, so we don't get 0 over 0, we'll have undefined slopes, which means there's vertical tangent lines. So except for this point right here. All right, so after you get those out of the way, then you can substitute in the other points one at a time, and then you may see some patterns sometimes, other times you may not. It just depends on what the derivative is. Okay? So let's say we start over here at the next point we need is 1, 0. So if you plug in 1, 0, 1 for x, 0 for y, well 1 for x, well 0 for y makes that 1 on the numerator. 1 for x makes that negative 1 in the denominator. 1 divided by negative 1 is negative 1. So at the point 1, 0, we'll have a slope of negative 1, which is like down 1, right 1. Not like that. Then if we try 0, 0, well, if y is 0, the numerator is positive 1 again. If x is 0, then you get negative 2 on the denominator, so it'll be negative 1/2. So here, this would be down 1, right 2, so it still has a negative slope, but not as steep as this one. Headed toward this point over here. And then finally, let's go negative 1, 0. So if y is 0, again, we get 1 on the numerator. And if x is negative 1, we get negative 1 minus 2, that's negative 3. So that's a negative 1/3. So it'd be down 1, right 3. So this is still negative, but even less steep than the other one. So these don't have to be drawn perfectly, just be able to tell the relative steepness there. Now let's try these other 3 points. Let's try 1, 2. X is 1 and y is 2. Now when y is 2, we get negative 1 on the numerator. 1 minus 2 over x is 1. 1 minus 2 is negative 1. So negative 1 divided by negative 1 gives you positive 1. So 1, 2, the slope is positive 1, so up 1, right 1. Like that. Then let's try 0, 2. 0, 2, you'd have 2 on the numerator, so that'd give you negative 1 on the numerator, 1 minus 2. And 0 on the number, 0 minus 2 is negative 2. So you get positive 1/2. So you might be able to see a pattern here now. So it'd be up 1, right 2. Some of these have a little symmetry. Notice this was 1, this was negative 1. This is 1/2, this was negative 1/2. So since this was negative 1/3, we're probably going to get positive 1/3 here. But let's just double check and see. So if we plug in negative 1, 2, again, 2 makes the numerator negative 1, 1 minus 2. And we plug in negative 1 minus 2, that's negative 3. Negative to reduce that again, so you get 1/3. So just like we predicted, it is a positive 1/3. A little less steep than the one we just drew. Be like up 1, right 3. Okay. So once you've graphed those, that's your slope field. That means the graph of the original function would have to fit in here. These are showing you like the little tangent lines if it were to go through those points. All right, now let's take a look at some of the questions they might ask about this. Describe all the points on the xy plane for which the slopes are positive. That means the derivative, dy dx, which gives you the slope, has to be greater than 0. Now you can look at this to give you clues of where the slopes are positive, but a more exact technique, because you haven't graphed the entire xy plane, so you might not see everywhere just by looking at the slope field. So you're better off just looking at the numerator and denominator. So in order to be positive, both the numerator and denominator have to be the same sign. So just look at the, because you're divided. So you have to have 1 minus y, the numerator, has to be greater than 0. And the other one was, the denominator was x minus 2 is greater than 0. So in this one, if you add the y over, you get 1 is greater than y. If you flip it around, y is less than 1. You add the 2, you get x is greater than 2. So that's one possibility. Or, since they're divided by each other, they could both be negative, and negative by negative is also positive. So the other possibility is 1 minus y is less than 0, and x minus 2 is also less than 0. So this when you add the y, you get 1 is less than y, which means y is greater than 1. Here add the 2, you get x is greater than 2. Alright, so I'm just going to move this where I have a little more room. Box off a little space here. And now let's write our answer right here for this first part. So you could say all points such that one possibility is y is less than 1 and x is greater than 2, or the other possibility is y is greater than 1 and x is greater than 2. Whoops. Just realized I accidentally changed the sign here. That should be less than 2. So that would be your answer for where describing all the points in xy plane for which the slopes are positive. Okay. So if you looked at your slope field, you probably could tell this one, y is greater than 1, x is less than 2. Y is greater than 1, x is less than 2. You could probably get that, but because we didn't graph the whole thing, you probably would have missed this other one where y is less than 1 and x is greater than 2, because that part we didn't graph on our slope field. All right, and then similarly, when the slopes are negative, dy dx has to be less than 0, because it already gives you the slope. So here, when you have a fraction here, the only way we can get a negative is if one of these is negative and the other is positive. So one possibility is that the numerator is positive. So 1 minus y is greater than 0, and x minus 2 is less than 0. So that gives you, if you add the y, 1 is greater than y, y is less than 1. And x is, you add the 2, less than 2. And then the other possibility is that the numerator is the one that's negative. 1 minus y is less than 0. And it's the denominator that's positive. X minus 2 is greater than 0. So then when you add the y, you get 1 is less than y, so y is greater than 1. Add the 2, x is greater than 2. So here we've got a couple possibilities. You could say all points such that one possibility is y is less than 1 and x is less than 2. Or the other possibility is that y is greater than 1 and x is greater than 2. All right, you could also be asked to describe all the points in the xy plane for which there's a horizontal tangent line. So notice we kind of already figured that out a little bit when we were graphing it. That's when the derivative equals 0. In other words, it's a numerator, you get 0 over something. So we kind of already saw that. We can just basically write what we put in our table here. That's when the numerator is 0, when y equals 1, and as long as the denominator is not 2. So here we can just word it. All points such that the numerator equals 0, so y equals 1, and x does not equal 2. And similarly, for vertical tangent lines, that's when you want the derivative to be undefined, which means you have some number that's not 0 divided by 0. So it's the denominator 0. Again, we've kind of already put in our table here. To get vertical tangent lines, we want the x-coordinate to be 2 to make the denominator 0, and the y-coordinate not to be 1. So they're not going to get 0 over 0. So it's the other way around. So you can say all points such that this time we want the new denominator to be 0, so x equals 2, and y does not equal 1. All right, then the next part says let y equal x be the particular solution. Notice it doesn't ask you to find it, though. It asks you to find it. That's where you'd have to separate the variables and integrate both sides, and then use this point to solve for c. But here, notice what it's asking for is something that takes a lot less time here. All it's asking for is to write an equation for the tangent line of f at x equals 1. So the tangent line, you need two things, remember to write, point of tangency and the slope. The point of tangency they give you right here is 1, -2. And then the slope comes from the derivative. That just comes from dy dx, substituting x equals 1, y equals -2. Now sometimes you might have already found it when you graph the slope field, 1, -2, but in this case that's not one of the points we found the slope of. So you just have to substitute those into the derivative. So we'll plug in y equals -2, so it'll be 1 minus -2 over x is 1, so 1 minus 2 gives you 1 plus 2, that's 3 over -1, so you get -3. There's the slope of our tangent line. So now we can write down our tangent line in point slope form. Would be y minus the y coordinate, which is -2, becomes +2, equals the slope was -3, times x minus the x coordinate is 1. Okay. Then it says use the tangent line found above to approximate f of 0.9. So we just have to substitute in 0.9 for x. Notice that's really close to our point of tangent at an x coordinate of 1. This is where we use local linear approximation, which is using the tangent line to approximate. So we just have y plus 2 equals -3, 0.9 minus 1. -0.9 minus 1 is -0.1. That's -3 times -0.1 is negatives cancel out, positive 0.3. And then subtract the 2. Y equals -1.7. So that's the exact point of the tangent line, which is an approximation for what we're looking for. So f of 0.9 is approximately equal to -1.7. All right, let's take a look at two where they actually give you the slope field. And when they give you the slope field, they tend to graph at a whole bunch of points like this. So it's easier to see. Notice not just the integer points, exactly what the graph will look like. And when it says, here's the slope field, here's our derivative right here. That's what's graphed here, the slope at each of these points using this derivative. And it asks you to sketch the solution curve. So the solution curve that goes through this point is one that would fit in our slope field, where these are the tangent lines. So start at the point you're given. Otherwise, you could start really anywhere if it didn't tell you that, but usually it will, otherwise there'll be too many possible answers here. So it goes through this point. And then what you do is you use these as like a guide. You go with the flow, because these are little tangent lines. So what you don't want to do, if you know you're going the wrong way, is you don't want to cut through these. If you're cutting through them, you're not going parallel to them, then you know you're definitely going the wrong way. What you want to do is keep your graph as parallel as you can to the closest, because these are tangent lines nearby. So I can see on these, there's kind of a slight negative slope. It's okay if you go over the top of them, as long as you go right over the top, because that means you're making it parallel right to that line there. And then just keep graphing here. It gets a little steeper, a little steeper. It's not an exact science, just up the best you can there. And then as you head this way, notice the slope start to get a little positive, and it levels off about there. And then they start to become more negative, levels off there. Oops. It's positive, and then you stop once you exit the slope field. You don't draw an arrow because you don't know what's happening beyond what it shows you there. So there's a sketch of what the solution curve could look like. The graph of the original function that has this is the derivative that would fit in our slope field. Because that's what the slope field gives you. A visual description of the different possible graphs you could get for the original function based on the slopes of the tangent lines that come from the slope field. All right, let's take a little one more of these. On this one, you've got a solution curve that goes through -1, -2. And here's your slope field right here. So -1, -2 is right there. And then you just, again, follow the slope field from there. So it kind of curves up like this. Oops. Notice this, the slopes are getting steeper this way. Just try to follow them up there and out. And then this way. So it's kind of like a parabola-like shape. Just try to follow those close as you can to the ones that are nearby, as parallel as you can make it there. So that would be the solution curve that goes through this point. All right, now let's take a look at some where you're trying to match the slope field with a differential equation it could represent. So here, these are the slope fields, and these are the derivatives here. So what you might want to try to find first is in the horizontal and vertical tangent lines. So if it has a numerator and denominator, set the numerator equal to 0. That gives you x equals 1. And that means that's where you'd have horizontal tangent lines. And if you set the denominator equal to 0, you get y equals 0. That's where you'd have vertical tangent lines. So x equals 1 horizontal tangent lines. We can look right here at this first one. You can see, well, this one's horizontal, but not the rest of these. So that doesn't work. The next one, x equals 1 horizontal. Again, right here is horizontal, but not at the rest of these. X equals 1. Okay, these are horizontal at x equals 1. And y equals 0 vertical. Now, it's a little hard to see where y equals 0, but these look like they're vertical right there. And this last one, x equals 1, they're not horizontal. So this one, 3 would go with A. All right, let's take a look at the next one here. Again, I'll just circle them here so you can see. There's where x equals 1, the horizontal ones, and where y equals 0, we've got the vertical ones. All right, on the next one, we set y equal to 0, and you get y equals 0. That's where we'll have horizontal tangent lines. And then set the denominator equals 0, you get x equals -2. That's where we'll have vertical tangent lines. So when you have y equals 0 horizontal, you can look at this one where y equals 0. Those don't look horizontal there. And this one, y equals 0, don't look horizontal. This one they do. And then x equals -2 vertical. Those look vertical there, so this would match up with that. There's y equals 0 horizontal, and x equals -2, we've got vertical ones. Okay, so this one matches up with B. And notice C, it's a little bit different. This one is in a factored form, so it's a little easier if you notice there's no denominator, so we're not going to have any vertical ones. So if you set that equal to 0, you can factor out an x, and you're left with y plus 1. So there's actually two different things where you'd have horizontal ones. Either the x equals 0 or y equals -1. those would both be horizontal. And since there's no denominator, this derivative can never be undefined. So this one has no vertical. So x equals 0, y equals -1 horizontal. So x equals 0 right here. Those don't look horizontal. X equals 0. Okay, those look horizontal. Y equals -1, also horizontal. So this one seems to fit. There's x equals 0, and there's y equals -1. So this would fit C. And then I know it's matching so that we know which one goes with that one here, but let's just see why it does. So if you set this equal to 0, you get y equals 1. Oops. We'll have vertical. This one does have a denominator. Sorry, we'll have horizontal, my bad. Numerator 0. This one does have a denominator, but notice there's no x's there. It's just a constant. So there's no way 2 is ever going to be 0. So this one also has no vertical. It's for a different reason. Not because there's no denominator, but because the denominator is never 0. So y equals 1, horizontal. You can see this one does have that. Now, a lot of times that's enough to figure it out. If there's still more than one possibility, some that have the same horizontal and vertical tangent lines, then all you have to do is pick one point where on one graph the slope is positive and the other graph the slope is negative, and then plug it in and see which one actually gives you the right slope. Sorry about the bell there. All right, let's look at one more matching one. On this one, the difference here is you're not matching it with the derivative, you're matching it with the original function. So you're basically trying to see kind of like these. Which of these functions, if you were to sketch the graph in here, would fit in the slope field? The difference is we're not given a specific point to plug in. So keep in mind that all these could be shifted up and down with a plus some unknown constant. So I'm just going to do the basic, and that's why we get all these different possible graphs. Do the basic graph of each of these to see which one would fit in. Oops. So y equals -x. Well, that's just a linear one with a slope of -1. About like that. So let's see if that would fit in our slope fields here. So on this one, you can see, oh, that's cutting through those, so that's definitely not going to fit that one in there. This one, you can see, it does fit in there. And notice the plus c would just shift it up or down, so it could be here and here. So I'll graph that in here so you can see that it fits right in there. So this one matches up with A. And then this one you can see is the -x squared. That's a parabola. It opens down. Oops. So the graph will look something like this. Yeah, I'm just graphing it with a c of value of 0 on all these, so it looks something like this. Again, the plus c could shift it up or down. So if you look at this one here, you see this part looks like maybe, but when you go this way, see it's cutting through the wrong way, so that's not it. This one looks so doesn't look good here because it's not leveling off. That doesn't look good here. Same thing with this one actually. This one though, you can see it does level off there, it looks like, and then does curve down this way, and then does curve down that way. So this one fits B. And then e to the x, remember that our exponential graph looks like. If you don't know what the graph looks like, you can just plug in some points to see what it looks like, and then see which slope field it would fit in. So e to the x, remember, goes through 0, 1. There's no shifts involved, and then it curves up like that. There's a horizontal asymptote right here. So let's try our main choices. This one, this part looks okay right here, but notice here these should be a lot more leveled off. They're way too steep right down here, so it doesn't fit in there. But this one, notice that you could do look like they level off so much that they're almost zero, and then this side does get steeper like the u of the x graph. So that's C. And then remember tangent, it kind of looks like the x cubed graph. Except it's got vertical asymptotes. What's the color on those? At negative pi over 2 and pi over 2. Because those are the places where cosine is 0, making tangent, since it's tangent sine over cosine undefined. So the graph kind of looks like this. Kind of like the x cubed graph, except x cubed graph levels off more there and doesn't have the asymptotes. So you can see on this one, that does fit our tangent graph, so that would be D. But again, if you're given any equations where you don't know what the graph looks like, just plug in a few points to see what the graph looks like, and then you can see if it fits in the slope field. And that concludes the notes for AP Calculus on the topic of slope fields.